Today's lesson marks the transition from 2 dimensions to 3 dimensions in terms of drawing lines and understanding lines. A line in 3 space is very, very similar to a line in 2 space, except that there is no scalar equation of a line in 3 space. And to understand why, let's remember that when you draw a line in 2 space, so ax plus by plus c equals 0, and then you draw a vector that's just the components of the coefficients there, you create what we call a normal vector. That vector is perpendicular to the line, and every line has a specific normal, not in the sense that the normal can have different lengths. Like, for example, the normal here, 6,4, is also a normal. The normal, n is -3, -2, is also a normal. That's not what I mean, but all of these are parallel to one another. So every normal to this plane is a scalar multiple of the same vector, right? And so a line has what we call a unique normal. Now, when you move to 3D, right? So remember, how do you make a vector? You make a point. So here's a point, 1, 2, 3. That causes that point to appear. And then I made up a direction vector, -2, 1, -1. And then I told it to do a line with this point and with this direction vector. And you can see what it does. It gives that point plus lambda, which we're using t, but whatever, you can use lambda if you want, times this direction vector. And all the points along this line would be expressible using that equation. Now, it doesn't seem like it's any different, because you can easily make a normal to this. Let's make a normal. What we would do is we would say, all we need to do is think of a vector that would dot with this to make 0. So 1, 2, 0, right? Would dot with m to make 0. -2 times 1 is -2, 2 times 1 is +2, and -1 times 0 is 0. You add them all up, you get 0, right? So let's make a vector from A to a point that's A plus that vector, and then we'll divide it by square root of 5, just to keep it a unit vector instead of a okay, and okay, we can see what happened. It drew a little vector, and that vector is perpendicular to the line. So why can't we use a scalar equation that has these components? The problem with this thing that I've drawn is not that it doesn't exist. A line has normals, right? The problem is that a line has way too many normals, right? There's actually an infinite number of normals to this line, right? All of these vectors, and I could have it draw more if we wanted. I mean, you can imagine you could draw thousands and an unlimited number, right? There'd be an unlimited number of vectors that are perpendicular to the line, right? In the same way that if you think of this as a bicycle tire, every spoke is perpendicular to the axle, right? And there are many spokes. So you can't create a line in 3D, because when you go ax, or so let's go 2x, no, let's do it this way, -2x minus plus y minus z equals 0, you just don't get a line. You get a plane. And it should be noted that this plane has an interesting relationship to the direction vector, right? Which is that the plane is perpendicular, but the line is perpendicular to many things, right? Anything on that spoke would be perpendicular to the line. So don't worry about the plane for now. That's next unit. I just wanted to demonstrate why that equation is not going to be coming with us today, because a line does not have a unique normal. In 3 space, a scalar equation defines a plane. And a plane is like, the analogy to a plane would be just a piece of paper. If you put a piece of paper on your desk, and then you stick a pencil on it so that the pencil points straight up, the pencil is the normal, and the paper is the plane. Everything on that plane is perpendicular to the pencil, right? So the pencil is a normal because it's perpendicular to everything. On the line, you have a normal, but you have many normals, so how do we know which one to use? Okay, vector parametric and symmetric equations. Now there is a new type of equation today. We don't use it super often, so just make sure you flag it in your notes. If I ask for it, you know where to go back and look. Again, the vector equation is the exact same thing. You find a point on the line, you find the direction vector of the line, and you add the point to some scalar multiple of that direction vector. So again, xyz is xo, yo, ro, where this is a point that you know, and then t times the direction vector of the way the line is moving. The parametric equations are the same. You're just doing one component at a time, and it's really no different than what you were doing in R2. You just have to have a third component, z. So you know how in R2, if we wanted to check if something was on a line, we would try to figure out t. You do the same thing here. You plug in a value for t, see what x would need, see what y would need. If they are the same, then you go on and check what z would need. If all of them need the same t, then yes, you're on the line. If any of them require a different t, you're not on the line. Now the symmetric equation is a new type of equation where all you're doing here is you're taking each parametric equation and isolating t. So since t has to be the same in all of them, we could move xo to the other side. So we go x minus xo divided by m1 is equal to t, right? And the same thing would be true of y and z. And so all three of these are, it's another way to think about how a line could be represented. As usual, the whatever you're subtracting on the top is the point, and whatever's in the denominator is the direction vector. Okay? Notice for the symmetric equations, you can't have 0 as a direction vector. Yeah, I mean, it says if one direction is 0, state the value of RO, while if two direction numbers are 0, there are just no symmetric equations. So I would say, yeah, if there are zeros, you can, I think what they mean here is, let's suppose that, z, okay, I think I get what they're saying here. So let's make up a line. So let's say our line was 1, 1, 1 plus 1, 0, 1. And this was, actually this is a bad example. Let's use 3, 2, 1 so we can tell them apart. And then let's say this was 5 and 4, just so we have all different numbers. What I could say here is that t is equal to, right, the x of your point, subtract the x of the known point, divided by 5. Okay? Or it would also be equal to the y, right? So y minus my known point divided by 0 equals z. Sorry, I meant z. I just wrote the wrong thing. Okay? And what happens here when you do this? Y minus 1 over 0, it really doesn't, you can't do anything with that. Although, what you can do, right, and the reason what they're talking about here, this again is not written especially clearly, but what you could say is you could get rid of this, okay, and then what you do on the side is you just say y is always 2, right? Because look at the equation. The point is 2, and it doesn't move. The direction vector doesn't move in a y direction, so you can kind of sort of get around this when there are two of them. If there's, if more than one of them are 0 in the direction, then just don't bother with the symmetric equation. You can kind of get around it if one of them is 0 by just doing this. Okay, find all possible equations for this line. It passes through these points. Okay, so remember, A line requires two things. It requires a known point. So for the purposes of our example, let's use 2, 3, -4. It would make no difference if you used 6, 1, 5. And a direction vector. Now, a direction vector here would be OP, right? Because, or P, let's say PQ. I don't want O because O makes you think the origin. It would be a direction vector PQ, which would simply be 6, 1, 5 minus 2, 3, -4, right? Which is 6 minus 2 is 4, 1 minus 3 is -2, and 5 minus -4 is 9. So there's a direction vector for the line. Notice, if I had done it the other way around, I would have got the same thing, but just negative. And since we're multiplying this vector by a scalar that can take on many values, it doesn't matter if it's positive or negative. So the first thing we could say here is that the line is equal to 2, 3, -4 plus t 4, -2, 9, where t is some real number, right? And again, unless I've made some error, I guess I could quickly check to make sure I did not make an error, but unless you make some error doing that, that's all you're ever going to have to do for this. So let's make a point A, 2, 3, -4. We'll make a point B, 6, 1, 5. We'll make a vector A to B, and then we'll make a line that passes through A that has vector U. And again, what does it do? 2, 3, -4 plus lambda 4, -2, 9, right? So exactly what we said. Now, mind you, this is not unique, right? There could be more than one answer here, but if I make another line, let's say that passes through B with vector U, you can see it's a quote different equation, although when you actually look at it, the lines are identical, right? So there's line F. So there's neither of them. Oh, sorry, I'll get rid of the vector maybe. Okay, there's line F, and there's line G. So, they're exactly the same thing. So, there are many ways to give the answer here. Marking it is kind of a pain because there are many ways you could write this and it would still be right. So I end up having to do a lot of testing. But whatever, that's my problem. It's not yours. So obviously, if there's a simple way to do it, I appreciate it if you do the simple way, but any way that works will work, and you'll get credit for it. Okay. Anyway, that's how you could do it as a vector. Now, to make a parametric equation, what we normally do is this. Okay, so you start a bracket. And then I think you can do this with a matrix on here. And then you give 3 for each. So x equals, y equals, z equals, right? So that just how I would like to see the parametric equation written. So you do L1, or whatever your line is called. You do a big curly bracket, and then x, y, z. So the x parameter would be given by 2 plus 4t. The y parameter would be 3 take away 2t. The z parameter would be -4 plus 9t. And again, in all of these cases, t is in the real numbers. T is a real number somewhere. Just try and line this up so it looks a bit better. Okay, so something like that would be, good for what this should look like. Okay, that's how you do the parametric equation. Now, the symmetric equation, I always try to remember this. It is the variable minus the point divided by the direction vector. Okay, so to make the symmetric equation, I go L1 t equals. Okay, then I go x minus 2 over 4, which is equal to y minus 3 over -2, which is equal to z plus 4 over 9. Okay, and any point that works on either of the other two should work in this one. So again, an easy test for this would be to test 615. Okay, so let's test 615. So so let's test. T equals 6 minus 2 over 4, which is equal to 1 minus 3 over negative 2, which is equal to 5 plus 4 over 9. And, you can pretty easily see here that this is t is equal to 4 over 4, or negative 2 over negative 2, or 9 over 9. In all cases, it's just equal to 1, which makes sense because this point, 615, is one direction vector away from the original point, 2, 3, negative 4. Okay? So again, just how you could use that equation, that's how you use it. I don't find many people use this one if they have the choice. I don't think you need to spend a lot of time emphasizing it, but again, you will be asked for it to do it at least once or twice, so just make sure that you've got some sticky or something that you can refer back to this part. Okay, find all possible equations for the line that passes through this and is perpendicular to that. Now, this is kind of interesting. So it's perpendicular to this vector and this vector. Okay, so remember, to create a line requires a point, which we have, negative 1, 3, 2, and then it requires a direction vector. And all we know about the direction vector is it has to be perpendicular to A and B. Okay, now you know how to make something that's perpendicular to A and B. It would be A I tried to times, okay, the cross product, right, would give you a vector that's perpendicular to both. Now remember, there is no such thing as a correct or unique direction vector, because any scalar multiple of the same direction would all work. So you don't need to worry, should it be A cross B or B cross A, or what about the magnitude or anything like that. Just cross the vectors and you will know what is perpendicular, right? And then you'll be able to do this. So let's see if we can work this out. So remember, let's try and remember our cross product here. Oh, yikes. Okay, our cross product says we start with the middle coordinate, then the last, then the first, then the middle again. Underneath that, negative 1, 2, 2, and negative 1 again. And now we just go through a series of x patterns. 6 plus 4, right? 8 plus 2, and 1 take away 6. So 10, 10, and negative 5. Now again, if I'm with it, I'm going to reduce this down to 2, 2, negative 1. There's no reason you don't need to, but it makes my calculations easier if I reduce the direction vector, right? Again, not necessary, but I'm going to do it. Okay? Now, what I'm suggesting is that the line that we're looking for, L1, is, and then you do a colon, right, is negative 1, 3, 2, plus t, 2, 2, negative 1, where t is some real number. Okay, let's test this theory. So I'm going to make a new sheet. Okay, let's draw the two vectors they gave us. So the point and then the vectors. So A is negative 1, 3, 4. Okay, so there's vector A. Again, many things are perpendicular to vector A. Then you have 2, negative 1, 2, which is B. Again, many things are perpendicular to B, but only one thing is perpendicular to both of them. And again, we get that by crossing A and B. It comes up with 10, 10, negative 5. Right? I reduce that by a factor of 5. It's an optional step. It's not required, but it's a good habit to be in. And then I'm going to go, the point that we know that it passes through is negative 1, 3, 2. And we need a line that passes through P that has a direction vector V. Okay. Now this line, right, it's perpendicular to both of the two vectors we started with, and it passes through the point we wanted. And again, if we're not clear on that, I think you can go angle FA So it needs a vector, not a. You can't do a vector in a line. Okay, so we'll do I mean, I guess this kind of defeats the purpose, but let's do the angle between our vector u and a would be 90, and then our angle between our vector u and b is also 90, right? So they're both meeting at 90 degrees, and we have a line that goes through as requested. Again, to finish this off, we should put it in the correct format, so I'm just going to copy paste this to save me a bit of time. The x-coordinate for our line, again, I kind of do this like this, right? Replace with the point. So I put in all three values for the point, and then I put in all the values for the direction vector. Right? So I try to think of it as everything that's alone is the point, everything with the t is the direction vector, and that's that. Okay, again, the symmetric equations is really just a case of just remembering where the stuff goes. So the point goes on the top. X, y minus 3 is still right over positive 2, and z minus 2 divided by negative 1 would be your symmetric equation for that one. Okay, and again, just double check it here. So positive 1, negative 3, negative 2, positive 2, positive 2, negative 1. Yeah, there you go. Okay, so good. All right, it has to pass through negative 2, 1, 3, and it has to have a y-intercept of 4. Okay, so the first thing we know is that P is negative 2, 1, 3. The next thing we know is that Q is 0, 4, 0. Remember, y-intercept means where does it hit the y-axis, and if you're hitting the y-axis, x must be 0 and z must be 0, right? So again, just to visualize that to help us understand, the point P was negative 2, 1, 3. The point Q was 0, 4, 0. And you can see that that is indeed a y-intercept, right? It's down there on the y-axis, and it passes through 4. Now again, making a line here is not difficult. All you got to do is vector P to Q, or vector Q to P, doesn't matter, and then line with either point and that vector, right? So negative 2, 1, and 3, or the other point, plus the direction vector. So again, all you're doing there is you just do, I'm just going to write mvec equals destination minus origin, and that the line, it would be equal to negative 2, 1, 3, plus t 2, negative 3, negative 3, where t is in reals. Okay, 2, negative 3, negative 3, is that what this did too? Oh, sorry, I think I messed this up. Right, sorry, this should not be negative. To get from negative 2 to 0 is 2, to get from 1 to 4 is 3, to get from 3 back down to 0 is negative 3, right? So you have that. Again, just do a quick copy paste for this. So, I'm sure you're getting the idea. 2, 1, 3 is the point. The direction vector is 2, 3, negative 3. Again, let's do the point first. The point goes on the top, plus 2, minus 1, and minus 3, and then the direction vector goes underneath 2, 3, and negative 3. Again, it should be easy to test a point. Let's test if 0, 4, 0 is on here. In order to make this 0, or when I plug in 0, 0 plus 2 over 2 is 1. When I plug in 4, 4 minus 1 is 3 over 3 is also 1. And when I plug in 0, I have 0 minus 3 over negative 3, which is also 1. So I know I did that right. Find the direction cosines and direction angles for the line defined by this parametric equation. Now, the direction cosines and direction angles, okay, let's just go back and remember what that was. What we said back in the previous unit was UVec is equal to U1, U2, U3, right? So there's, a vector has 3 components, right? and that if you took u1 over cos alpha, you would get is the direction, or the direction, I'm sorry, I've written this wrong, sorry. u1 over the magnitude of u is equal to the direction that this makes, or the angle with the positive, with the positive x-axis. Okay, and again, the same thing would be true for beta and gamma. So beta would use u2, and this would use u3. So to do this, right, understand that the direction, any line is parallel with its direction vector. Therefore, its angles are identical to those of the direction vector. So in our case, we're going to make m. M, you can read from the equation, is -1, 3, 2, right? Because it's basically everything that's attached to a t. Okay, the magnitude of this would be root 14, right? Because 1 plus 9 plus 4. And so what we would say here is that the direction cosines, let's write the three direction cosines. So cos alpha is equal to -1 over square root 14. Okay. Cos beta is 3 over square root 14. Oh. Just copy paste this maybe. Forgot my little escape character. Okay. And cos gamma is 2 over square root 14. Okay, and that's it. And then all you would need to do here is just inverse cos and get the angles. So let's demonstrate this by we'll go here. let's draw the line first. So it passes through 2, 0, 0, right? And it has a direction vector of -1, 3, 2. And we go line AM, and that's it. Now the angle this makes with the positive x, y, z axis. So here's what I'm going to do. I'm going to make a new vector. It's going to be A. It's going to join A and 1 point over on the x-axis. Okay, so that's kind of like the angle it makes with the positive x-axis if I did the angle between that vector and the direction vector. Okay, I'm going to make another such thing, except I'm going to make it parallel to the y-axis, so it's going to point towards us, and then another one that's parallel to the z-axis is going to point straight up, right? So what angle does our line make with any of those vectors? So I don't know. We'll see if this works. MU. Yeah, but it would be nice if we could actually show it over here. I guess I probably shouldn't have done it this way. Okay, let's just quickly make the points. So 0, 3, 0. Sorry, 3, 0, 0. X is red. 2, -1, 0. 2, 1, 0. And 2, 0, 1. Okay, so if I go angle, so let's do the x one first. So B to A, and then the other point will be A plus M. Okay, so there's the angle it makes with the x-axis. Okay, so that 105.5 there would be the same thing as if you did inverse cos of -1 over square root 14. Right, that's just where that's coming from. It's just measuring that angle from the direction cosine. Again, if we were to do an angle from C to A to a point A plus M away, we get the other direction vector there with y is 36.7, and that would correspond to the inverse sine of, what was it, 2 over, no, sorry, it wasn't 2. Oh, there was 3. Sorry. Oh, inverse sine. I don't know what I'm doing. Inverse cos. Sorry. That was strange. Okay, and then finally inverse cos. So inverse cos of point D to A and then A plus M. It says know how to do inverse cos all of a sudden. Oh, right. Yeah, I'm sorry. Of course it doesn't. I'm tipping the wrong thing. Sorry. So D, A plus M. And the last angle there, you can kind of see the 57.69. That would be the inverse cos of the third, which was a 2. 2 divided by square root 14. And there's your 57.69. So all your direction angles, they work the same way as before. Just remember they work off the direction vector. They don't really have anything to do with the point. Okay, so the point really doesn't play a role there with that. Okay, so anyway, just quickly, let's just label what they all are. So this last one, the gamma, was inverse cos of 2, so it's 57.69. Oh, sorry, so I guess what I should write here is, so the direction angle would be that. For this one, we found that the direction angle beta was 36.7. And for the first one, because it was negative, we noticed it was negative, so that makes it obtuse, and it was 105.5. Oops. Okay, so that's that. Nothing else to do. So direction cosines are these 3 numbers, direction angles are those 3 numbers. Okay, find the angle between the lines. Okay, now the angle between the lines equals the angle between the direction vectors. Let's graph this, and I'm just going to show you what I'm talking about. So, okay, so just so I can type it in, we have a point A, which is negative 1, 1, 0. We have a point B, which is 1, negative 3, 5. We have a direction vector M1, that's 2, 1, 3. We have a direction vector M2, that's 2, negative 1, 1. Then we have line A, M1, and line B, M2. Okay, so let's hide the direction vectors, and those are the lines. Now, the angle between 2 lines, it's a difficult thing to understand in 3D because most lines, in 2D, 2 lines, unless they're parallel, are going to cross each other. Not really the case in 3D, right? Because you can have lines that are not parallel like these ones and nevertheless do not meet. So, the angle between the 2 lines, it kind of doesn't really, all it means is the angle between M1 and M2, between the 2 direction vectors. Which again is a difficult thing to even kind of appreciate from this picture. So let's just keep it. Maybe the demonstration doesn't really help there. It's just the angle between the direction vectors. So we know. Let's call them M1 dot M2 is equal to M1 2 cos theta, right? And cos theta is the angle between them. So all you're doing here is just manipulating this formula to go the cos theta. Okay, let's dot the vectors. So M1 is 2, 1, 3. We want to dot that with, so it's 2, 1, 3 dot 2, negative 1, 1. And that would be equal to 4 take away 1 plus 3, which is equal to 6. So, sorry, solution looks horrible. Okay, so we'll do the dot product there. We'll do the magnitudes are, let's see, square root of 14 again. And then the other one is square root of 6. 4 plus 1 plus 1. So on the bottom of our, so we're going to have 6 divided by square root 14, square root 6. Okay, so like that is going to be equal to cos theta. Okay, so theta, we just need to do the inverse cos. So 6 divided by square root 14 divided by square root 6. And then we do inverse cos of that. We get 49.11 degrees. Which is, of course, the same thing GeoGebra measured between the two direction vectors. So that's that. To find the angle between the lines, you just do the angle between the direction vectors. Now, a point to a line in R3 is a difficult one because if you remember our analogy in R2, so let's make up a random one. So A is 1, 1, 1. M is negative 2, 1, 3. And we'll go line AM. And we'll make up a point. Let's say the point is C equals 4, 5, negative 3. Okay, so there's the point over there. Now the question is, what is the shortest distance, okay, between between that point and that line? Now, once again, the answer is the same, right? It's we need to move in a perpendicular direction from C directly to the line. So you need a point on the line that so you need a point. Let's say we need a point B. Let's say such that B is on the line and such that BC dot BA is 0. That's a good way to solve it. So, one way of solving it is, let's just, I don't know if they actually do this. They don't do this. So, another method, hypothesize or suppose a point B is on the line such that AB I guess I should. Sorry, Q is a point on the line. P is any other point. So Q is the point on the line, and then P is the other point. QP vec equals 0. Sorry. Point Q is the point on the line. So QB dot Q dot BP. I'm sorry, it would be 0. If you can solve that equation, then the solution is the magnitude of BP. Right? So whatever the magnitude is between B and your point would have to be the shortest distance. Because you have a point on the line, it's perpendicular to the other point, which means it's the closest point you can get to. So if you just measure the distance from those two, you would get the answer. So I don't think that's a super way of doing it, although it can be good. Yeah, because all you got to do is plug this in, and of course QB is really just the direction vector of the line. So it's even a bit simpler than I made it out to be. You need to find a point B such that it, it would probably help me if I rename this. This is P and this is Q. So you find a point here that that's on the line, but that also dots with the normal to make 0. It can be done, but there's a much nicer way of doing it. Okay, and here's what I'm going to try to show. Let's make another point. Okay, Q plus M. Okay, so we have this point A. So we find another point on the line that is one direction vector away. Okay, and you don't even really need to do this. I just need to do this for the demonstration. Now, imagine you had a vector. So let's draw some vectors here. So vector O to A, or Q to A, and then Q to P. Okay. Now, these two, right? Actually, sorry, it would be a little bit easier if I made it move in the other direction. It doesn't matter for the solution, but the picture will look better if I do it this way. Okay. Now, these two, okay, imagine that they form a parallelogram. So we go P plus, or P minus M would be a point down there, and then we go polygon Q, P, what is that one? What did it give it the name? B, A. Okay, you make a parallelogram, and the height of the parallelogram would be the thing we need, right? Okay, I know this is kind of hard to see because I can't really. No, I don't want to do that. I'll do that. Okay, so what I've done, I've used a vector along the line and a vector that joins Q to the point we're interested in. You form a parallelogram, and the height of the parallelogram is the thing you need. Now, the height of the parallelogram, you might think like, oh, well, that's great. How do I do that? Except remember that the area of a parallelogram is, we know how to do that. It's the magnitude of the cross product. So this is a really brilliant solution, right? Let's recall. Let's try and write down how this works. So make a parallelogram using the direction vector and the vector PQ. Okay? The height of that parallelogram is the required distance. Okay? And we know that the area is equal to the magnitude of the cross product, right? So m vec times q. Okay, so the magnitude of the cross product. Okay, and now think about it. If you know the area, right, and we know that the area of a parallelogram is base times height, then we know the base. The base is just the magnitude of the direction vector. So where does this formula come from? What it does is it figures out the height, all right? Therefore, the height would be equal to the area divided by the base, and that's where they get the formula from. So you cross M and QP, you divide it by the magnitude of M, and that will give you the missing height in your picture. Okay, so let's show how this would work. So I mean, the parallelogram you can see here has an area of 19.44. So all we got to do is that Q1 divided by length M, and the answer is 5.2, 5.1962. Now, is there a way that we could check that? Okay, GeoGebra is excellent at checking this stuff. Look, distance, point, object. So I want to know the distance between the point P right? The point P and the line F, right? And there it is, 5.1962. That's how far away P is from that line. Now we can sort of show this if we draw a circle at point P with radius d and with the direction vector m. Okay, it draws a circle, and indeed that circle of that exact length contacts the line once, where it's perpendicular directly across from it. Okay, so again, what you're doing here, right, is trying to find how close P is to that line. The brilliant solution to this, again, there are other ways of doing it. You can use projections and other things. But the best way to do this is to understand this parallelogram method. The thing you want to know is the height of the parallelogram, but you know the parallelogram's area, and you know its base. So you can work out its height by simply dividing the two. Okay? Let's try... so this is the dot product method, where you the other one I was saying. So you make a generic point, you force the dot product to be 0, and then you figure out the point and get its magnitude. I don't even want to go through it. You should just use this method. There's very little reason to do this, but it's good. It's interesting. I mean, give it a try. But in your work, I would just stick to this one. This is so elegant. Okay, find the distance from this point to this line. Okay, so let's see if we can test this. So Q is the point off the line. P is a point on the line. Is that what we decided? No, of course I get this wrong. P is a point not on the line. So in our case, M is the direction vector of the line. And we actually don't even need... well, no, yeah, that's not true. Sorry, we do need that. Okay, so what do we need here? M. So let's start with Q. Okay, so vector QP is a vector that joins... It's simply a vector that joins the point you're looking for to any point on the line. Because any parallelogram that you draw would all have the same height. So QP, in our case, would be, how do I get from 0, 0, 0 to -1, -3, 2? Well, would be that, right? To get from Q to P, I would go -1 in the x, I would go 0 in the y, and I would go 2 in the z, right? And that would be that vector. Okay, because I'm just doing destination minus origin. Maybe I should actually write down what these are. So the point on the line is -1, 0, 2. The point not on the line is 0, 0, 0. And that makes Q really a position vector, just -1, 0, 2. The direction vector of the line is 2, -3, 0. And so the question is, how close is that point to the origin? Okay? How close is that line to the origin? Now again, the solution is draw a parallelogram and find its height. The parallelogram, is here. So that's the area of the parallelogram. The height, or h, or let's say d, I guess, for distance, would be this divided by length. Okay, and that's it. Right, so all we got to do now is cross the two vectors. So let's cross them. So we're looking at 0, 2, -1, 0, and we're crossing that with -3, 0, 2, and -3. Now zeros make an easy cross product here. You have 0 take away -6, you have 4 take away 0, and you have 3 take away 0. So 6, 4, 3 would be the cross product. The magnitude of the cross product would be 36 plus 9 plus 16, so 25 and 36 makes 61. Okay, and the magnitude of m is just 4 plus square root 13. So the answer is square root 61 divided by square root 13 equals the distance. So we can work that out. So let's do it. So square root 13, 61, sorry. Square root 61 divided by that number. So 2.17 units away. Okay, now let's draw it so we can show. So the P is a point that's not on the line, so P is just the 0, 0, 0 here. Q is the point that's negative 1, 0, 2. Okay, and then the direction vector was 2, negative 3, 0. So we go line with that passes through Q that has direction vector M. Now what's the shortest distance between that point and this point? Not point, sorry, that line. Yeah, sorry, it's the direction vector I want to get rid of. Okay, now my theory, right? Let's just go back here for a second. So k between 2 and 3. Okay, now watch this. Okay, we'll draw a sphere that starts at point P that has a radius of k. Now you can see that moving a distance of 2 is not enough to get you to that line, right? And moving a distance of 3 is too big. It's something shorter than 3. So let's scale it down. Now our hypothesis was the answer was 2.17, right? At 2.17, just reach that line. Right now, it doesn't actually intersect at Q, so try not to look at Q. Try to look like it's tangent. It intersects over here, right? Q is just... Again, you don't need to go through all of this. GeoGebra has a nice, easy way of doing this. All you have to do is type distance between the point and the object. The point is P. The object is the line F. The answer is 2.17. Okay? Don't tell the other class about this. But anyway, you can use it. No, I'm just kidding. Of course you can tell the other class. I think you should only use it to check your work, of course, but there it is. Okay, so 2.1, and just to compare, our answer, square root 61 over square root 13, was that exact number, right? It was 2.16617, 2.16617. If we set k to equal this number, and then draw our sphere again, then our sphere is actually perfect. It is perfectly tangent, reaches it at exactly that value. Okay, so that's the shortest distance between a point and a line in 3D. It's a bit different. You can't project onto the normal because there is no unique normal to project onto. You can't do what we did yesterday. Okay, I'm going to write that down just here. So this is method 2, but there's a note for method 2 underneath. I should have read ahead. You cannot project PQ onto the normal because there is no unique normal to a line in R3. Oh my goodness, in R3. So yesterday's method is out. Okay, but this method is just as nice and very quick. All you got to do is cross product, take the magnitude, divide by the magnitude of m, you have your answer. Okay, so that's, is this just a repeat, -1? It's just the same question again. Oh, just using the different method. Yeah, give it a try. I'm not going to do it here because this is already getting close to an hour, so I'll stop it. There's a bunch of extra practice here, and I will look to see if there's an assignment that opens with this material. Feel free to post questions or inquire if there's anything you need.